look at synthesis reactions today. We are going to reference the synthesis packet, and then we are going to look back at our Unit 4 reference sheet as well. The Unit 4 reference sheet is just going to help us to go back and look at what are the different reactions with alkenes and alkynes. I am going to hit on some of the key things up here as well. So the synthesis that we're looking at today is adding SN2, SN1, E2, and E1 to all of the Unit 4 reactions that we did with alkenes and alkynes. This is what organic chemistry gets to as you really dive into college organic, where you're continuing to build off of all of the different reactions that you've seen. So these tips for solving synthesis problems we saw in Unit 4. And so we're just going to go through these just to kind of remind ourselves, because we're going to use this again as we're looking at synthesis problems today. So start by counting your carbons. Does the chain get longer? Does the chain get shorter? Do we have to look at the cleavage reactions? Are we looking at chain elongation? If the chain gets longer, so some of the things that I have up on the slides I've kind of added in aren't necessarily on your slides, so like this one. If the chain gets longer, you need a terminal alkyne for chain elongation. So just a reminder, if the chain gets longer, you have to have a terminal alkyne for chain elongation. We can use our reference sheet. So what forms what? What functional group are we starting with? What are we ending with? Is it adding Markovnikov? Is it adding anti-Markovnikov? And we can work backwards. If we need to put a Br on carbon 4, where was the double bond at for us to put that bromine on that carbon? And then find patterns. So some examples, if we're making an alkane, we probably needed an alkene. Chain elongation requires a terminal alkyne in order to add more carbons to that. So maybe some new things that we're adding on to Unit 4. We started with a terminal alkyne and we added carbons to that through the chain elongation process. Well, we could actually think about it the other way as well. If you are starting with an alkyl halide is an alkane with a halogen attached. That's an alkyl halide. You can actually extend a chain. You can elongate the chain by actually having your carbanion over the arrow. So before, what we did is we had our terminal alkyne, and then we put an alkyl halide above the arrow. We can think about it the other way too. And we're going to see what this looks like when we get into the practice. When you add a carbanion alkyne, that's actually just substitution, because it's a strong nucleophile and a strong base. We did this in Unit 4, we just switched it, right? We started with the terminal alkyne and we added the alkyl halide. This is just SN2, where you're just substituting. So we're going to look at what this actually looks like when we do a synthesis problem. When you have bad leaving groups, so I say bad leaving groups because it's difficult for them to leave on their own, like halogens. Halogens are good leaving groups. That's why we usually see Br as a very common leaving group. Bad leaving groups are alcohols. So when you have an OH group, you have an OCH3 group. Those are, maybe we could use the term weak leaving group instead. They become better leaving groups when they're protonated. So you add an H plus to it, it becomes a much better leaving group, because then the electrons can go to itself and it leaving a carbocation, or just leaving to allow for substitution or elimination. And so if we have these bad leaving groups, so we see an OH attached or an OCH3 attached, what we can do is just add an acid. So above the arrow, we just put H+. That protonates the leaving group, makes it easier for it to leave. Right? It makes it a better leaving group. And then the other thing that we want to think about is how do we form the Zaitsev, which is the more substituted alkene, versus the Hoffman, so the less substituted alkene, to get the reaction or to get the product that you want. So are we looking for a more substituted alkene, or are we actually looking for a less substituted? We talked about less substituted alkenes being the E2 reactions with the bulky base. So if you want a Hoffman product, less substituted, we have to use a bulky base. We see tert-butoxide used often. Or what if we want to favor elimination over substitution? We talked in the do now about temperature. So we could then add heat or remove heat, right? Hot or cold temperatures. So this is just kind of thinking about everything we did in Unit 4 and then adding in some of the substitution and some of the elimination considerations as well. So what we'll do is we'll just look at some practice. Looks very much like the synthesis that we did before. We're going to go through the same process as well. So start. First thing to do, start by counting your carbons. So I'm going to use different colors up here as we go through. In my parent chain, 1, 2, 3, 4 carbons. So 4 C's in the parent chain, 1, 2, 3, 4. I look here, 1, 2, 3, 4 carbons in the parent chain. So both of these, we have 4 carbons in the parent chain. Notice you have the 2 methyl groups off of carbon 2, so we don't have to worry about chain elongation. Now what I want to do is I want to look at what has to happen. So we can see that this requires 3 steps. We see step 1, we get an intermediate. Step 2, we get another intermediate. Step 3, we get our product. And so now it comes down to looking at what's actually happening. So I notice that I'm removing this OH, and I'm adding a Br to this side. So I'm removing the OH, and I'm adding a Br to the other side. So if we remember from Unit 4, if I have an OH on this carbon and a Br on this carbon, I probably at one point had a double bond right here. Right? If I had an OH here, the Br is down here, there probably was a double bond here at one point. So if we think about what that is considered, Br is adding to the less substituted side. Yeah, Br is added anti-Markovnikov. To the less, well, we consider the leaving group leaving as one step. Yeah. So Br is added anti-Markovnikov. And with this, yeah, so this is, technically we might consider it 2 steps. We're showing 3 because we're going to show if a leaving group leaves, we're going to show that as a step as well. Like how do we allow it to leave? So we know that we're going to have to form a double bond here. So this is us kind of working backwards. If a double bond needs to be formed, we've now seen we have substitution and elimination reactions that allow us to go from an alkane to an alkene. A lot of our reactions on here went from alkenes to alkanes, or alkynes to alkenes, or alkynes to alkanes. All right. If we want to go the other way, that's when we're going to look at substitution and elimination reactions. Now, OH. Let's start by looking at OH here. OH and OCH3, these are weak leaving groups. This is a weak leaving group, which means it's going to be difficult for it to leave on its own. And so what we have to do, if it's a weak leaving group, we can protonate it. You add an H plus to it, it makes it a better leaving group. I'll show you why it makes it a better leaving group as we're looking at the mechanism. So if you have a weak leaving group, but you know that it needs to leave, you know that we need to get rid of that OH, we're just going to add acid. So we just see it as H plus. All right, so up here, we're going to add an acid. The reason, you don't have to write all of this when you're looking at synthesis. Oh, that's an O. When you're actually doing a synthesis problem, you don't have to write like the add acid or why we're doing it. It's just for this as you're looking through. So this is to protonate the leaving group to increase the strength, right? When I say increase the strength, it's now going to be more likely to leave on its own. So when we add the H+, we're going to have, so here's kind of our parent chain. If we look at this with an H+, not only are we adding an H, we're also adding a plus formal charge. Because now, instead of oxygen having 2 bonds and 2 lone pairs, it has 3 bonds and 1 lone pair. Now, this has become a better leaving group. Now, we say this has become a better leaving group, so now we're getting into, right, what's kind of this in-between step. The point of this leaving group of protonating it was so that it could leave. Now here, we know that we need to form a double bond. So I want to figure out how can I form a double bond, and we kind of have talked through where it needs to go. That double bond needs to go here. I'm just putting the dotted line because that's not part of our product. But the double bond needs to go here. Now we're going to think about substitution and elimination reactions. If we want to form a double bond, is that substitution or is that elimination? It's elimination. So we need to have an elimination reaction. Now look at where that double bond needs to form. Are we forming the more substituted or the less substituted alkene? Less, right? Putting it here is the less substituted. So need less substituted alkene. What product is that called? Hoffman. The less substituted alkene is a Hoffman product. Hoffman product forms when we use a bulky base. Right? Hoffman product forms when we use a bulky base. Or a strong non-nucleophilic base. Right? It's going to undergo an E2 reaction. So I'm going to put SNNB, that stands for strong non-nucleophilic base. I'm going to actually put potassium tert butoxide. Now you don't have to put the potassium. If you just did tert butoxide, that's fine, right? Because potassium is a spectator ion anyways. With this elimination reaction, again, because it's a bulky base and we're forming the Hoffman product, this is an E2 reaction. This is going to happen all at once. Notice you don't have to show the mechanism. You're just thinking about the reactants and then what that intermediate product is. What's going to happen is when this leaves, because this is going to happen all at once, the bulky base, because it's bulky, has to attack one of these beta hydrogens. Doesn't matter which one of those 3 it attacks, but the bulky base is going to attack one of these beta hydrogens because they're less sterically hindered. So the bulky base is going to attack one of these hydrogens, and then the bonding electrons will form that double bond. These bonding electrons will go to oxygen. Well, now that leaving group is H2O. Now it's going to leave and produce water. You don't have to put the side products once your leaving groups leave, but it's going to look like this. There's our alkene, our less substituted alkene. So most of this is what we've talked about already. Now this last step is where we might need to use our reference sheet. So we have an alkene. We need to get bromine added in an anti-Markovnikov fashion. Right, if you look at your reference sheet, so this orangish, yellowish, goldish sheet, if we start with an alkene, how can we get Br added anti-Markovnikov? Free radical addition. And again, I am not asking you for the mechanisms of this. I just want to know, all right, now what are our reactants? or what are our reagents? What's above the arrow? So free radical addition is HBr and peroxides. So this is kind of a practice synthesis problem where all we're doing is taking what we've done with substitution and elimination, putting it through, and then kind of combining in unit 4. Questions on this one before we look at another one? It's like a puzzle. Lots of lots of things we just have to kind of think about. So the next one, notice for these I'm giving you how many steps as well, but kind of go through the same process. So start by counting the number of carbons. If you count the number of carbons, I see that we have a cyclohexane. Are we changing the number of carbons between our parent chains in the reactant and the final product? Now, we have a cyclohexane, and then 1 carbon, cyclohexane, 1 carbon. So we're not changing the number of carbons, so we don't have to worry about chain elongation. Now we want to look at, okay, well, so then what do we notice about it? A lot of times people say, well, the Br moved. Yes. Right, the bromine moved. So the bromine was connected to this carbon. This was our alpha carbon. And then the bromine got removed and got added to a new alpha carbon. Now we can't just say, well, why can't we just move the bromine? You still are breaking a bond and forming a bond. You can't just move it. And so what we have to do is we have to see where can we go in the middle. We just have one intermediate here. So let's say, okay, well, what if I want the Br to leave? All right, bromine, halogens are good leaving groups. So let's say this Br left. What could we potentially put here that would allow us to put bromine somewhere else? Right, I could put a double bond. We could make an alkene, and then we could add the bromine to one side of the alkene. So let's here create an alkene. Well, we've looked at how do we get an alkyl halide to create an alkene. That's an elimination reaction. Elimination reaction. Now, in this case, it doesn't actually matter which set of reactants we were to use. But I'll kind of explain what you have to make sure to do if you use one over another. So the reason that it doesn't matter is because there's only one singular beta hydrogen here. Right? Because we don't use the alpha hydrogens. This carbon is the beta carbon. Has 1, 2, 3 bonds, so it only has 1 hydrogen connected. So it doesn't actually matter whether this were to undergo an E1 or E2. What does matter, though, right now technically you say, yeah, but you'd form a primary carbocation. You would, which means we need to make sure we have a strong nucleophile. Right, so we need to, strong base, right? We need to make sure we have a strong base. Now, does it matter whether you use a strong non-nucleophilic base, a bulky base, or just a strong base? No, it doesn't matter. You could actually have one of 2 sets of conditions. So you could use a strong non-nucleophilic base, right? Something like, I use potassium tert-butoxide or just tert-butoxide because usually if you just use one the whole time, that's fine. You just get used to it. So you could just use tert-butoxide. That undergoes an E2 reaction. And if you say, yeah, but that produces the Hoffman product, well, it doesn't actually matter because there's only one beta hydrogen. Or you could use a strong base. Most common strong base that we see is sodium hydroxide. Now, sodium hydroxide, really we're focusing on that hydroxide. That is a strong base. However, hydroxide is also a strong nucleophile. If I want just an elimination reaction to occur, how can I favor elimination over substitution? Temperature. So I could use sodium hydroxide and heat. That's going to push the elimination reaction to occur. So if I look at the product here, there's our alkene. Now I look at this and I say, okay, based on this alkene, I'm adding Br to the more substituted side. So Br is added in a Markovnikov fashion. So now bromine is added in a Markovnikov fashion. It's added to the more substituted carbon. So again, we look at our reference sheet. Remember, you get this reference sheet all the time. This is the only thing you get for the test. You don't get your flow chart. Just this. So you're taking an alkene and you want to add to the more substituted side. That's just your electrophilic addition. Right? Electrophilic addition is hydrohalogenation. So if I want to add Br, we're going to do HBr. All right, hydrohalogenation. So again, we're just kind of combining what we've done with elimination. The thing with this is we want an E2 reaction to occur. Right, we want E2, which is single step. It doesn't matter which one we used because there was only one beta hydrogen. So the Hoffman and the Zaitsev product were the same. If you wanted a more substituted, you wanted the Zaitsev product, you would have had to use NaOH and heat. If you wanted only the Hoffman product, you would use your strong non-nucleophilic base. You'd use your bulky base. So again, kind of looking at combining our elimination with our Unit 4. So I think, oh yeah, okay, now we'll look at this one. So now we have it where I don't give you the steps. I'm going to tell you the steps though. Like I'll give you a hint on how many steps there are. And we're going to go through this one. I think this might be the most difficult one. Only because when people think that we need chain elongation, they think that it's the first thing that absolutely has to happen. And that's not always the case when we start to tie in other reactions. So if we take a look at our reactant compared to our product, start by counting your carbons. Right? 1, 2, 3 carbons. So the starting reactant has 3 carbons. Final product. 1, 2, 3, 4, 5. So our final product has 5 carbons. Now I notice the other thing is that there are 2 products. What is the functional group when you have COOH? So this actually forms 2 carboxylic acids. So I notice that I have to elongate the chain. I also notice that the product is 2 carboxylic acids. So what I want to do, and sometimes it just helps as you're looking, to look at your reference sheet again. So I notice that I need to end with 2 carboxylic acids. So I kind of read through everything. Remember that cutting a bond is a cleavage reaction, right? Like a cleaver is a knife. So cleavage reaction is cutting a bond. And so I'm looking at the cleavage reactions down here that produce 2 carboxylic acids. All right, so I notice that I can have ozonolysis produces 2 carboxylic acids, and so does permanganate oxidation. Right? They both produce carboxylic acids. But to produce carboxylic acids, it has to start with an alkyne. So these products come from an alkyne. Now this synthesis reaction, just to kind of give a hint, is 3 steps. So we're going to have 3 steps. Step 1, I'm going to put my dotted line. Step 2, and step 3. So I know that to produce 2 carboxylic acids, this step 3 is going to come from an alkyne. It's going to be one of the cleavage reactions of an alkyne. So now I have to kind of work backwards from there. So I know that here I need to produce, so let's do this. This needs to be an alkyne. Right, kind of working my way down and around. So I gave a hint of 3 steps. So step 1, we don't know what the intermediate is. Step 2, don't know what the reactants are, but we know that we're producing an alkyne. And then step 3. So sometimes you have to kind of work your way backwards like this. Now, I don't have a way to go from an alkene to an alkyne. I don't have a way to go from an alkene to an alkyne. We have a way to go from an alkane to an alkyne though. Because what we could do here if we have an alkane is we could do a substitution reaction. A substitution reaction is chain elongation. So I know this kind of looks weird up here, but we're kind of working backwards as we go through. So I want to take a double bond, I want to take an alkene, and I want to go to an alkane. Now, in order for me to have a substitution reaction, right, in order for us to have a substitution reaction, we need a leaving group. So I can't just use hydrogenation and get rid of the double bond. We need to put a leaving group onto the alkane that we're creating. Now, if we kind of think through the steps that we're doing, we need a substitution reaction and we need to add a triple bond. That's chain elongation. But we have to make sure that we add the triple bond to the end. So when we're creating this alkane, I need to make sure that I put a leaving group here. Right? I put LG for leaving group. So now we're starting to think about, okay, I want to add a leaving group. A good leaving group is a halide. Br is the most common that we see. So if I want to add, let's say Br to this side of the alkene, I'm adding it to the less substituted side. All right, we looked at this already. It was the free radical bromination. So free radical bromination is HBr and peroxides. So this, all right, free radical bromination. Use a different color here to draw our alkane. So I still have the same number of carbons, 1, 2, 3 in the parent chain, 1, 2, 3 in the parent chain with the methyl, but now we've added a Br here. You need to add the leaving group to the less substituted side because now if you have a substitution reaction, we can substitute a triple bond. You can actually substitute a triple bond in for a leaving group. Now, I want to go from 3 carbons to 5 carbons. A nucleophile that you can use is a carbanion. I want to add 2 carbons. So I can have this negative carbon, but it needs to be triple bonded to another carbon. I need to add 2 carbons. So what's going to happen is this negative, Right, nucleophilic substitution, this negative, these electrons are going to attack this carbon. That's going to form a single bond, and your leaving group is going to leave. And then the alkyne that we create, 1, 2, 3, 4, 5, looks like this. So again, this leaving group is going to leave because this carbon is going to come in, act as a strong nucleophile, and attack that alpha carbon. You had 1, 2, 3 carbons initially, 1, 2, 3, 4, 5. Because there's 2 more carbons here that are being substituted in. Now when you actually look at your reference sheet, you could use either one of the cleavage reactions. I think the first one that people see on the list is ozonolysis. Right, ozonolysis adds ozone and water and zinc. So O3 and H2O and Zn. So I guess technically you could have 3 and 4. This is a cleavage reaction. Cleavage reaction will actually cut this triple bond and produce that carboxylic acid. It's going to produce 2 carboxylic acids. You didn't have to know the mechanisms for them before. You still don't have to. But this just gives you some ideas for the synthesis. It's lots of problem solving, lots of looking at everything.